hey, thought I'd do a video on position, velocity, acceleration, speed, and displacement. So I drew a graph right here. I labeled my y-axis in centimeters and my x-axis in seconds. I expanded the scale a little bit just so you could see it a little easier. And this position graph is telling us about a particle that starts at home, whatever that is, and for some reason this particle can only move exactly right and exactly left. So it's moving on a horizontal line. So what we see here, and getting these ordered pairs is helpful, we see that at 2 seconds, the particle's position at 2 seconds is 2 centimeters away from home. So we know at 2 seconds our particle has gotten to here. Then at 5 seconds, our particle is at position -3. So what our particle did is it went here, and then, first thing it did is went here, and then it turned around and went back here. Then it doesn't change position for the next 2 seconds. It just hangs out. Then when it moves again, it moves from position -3 and goes beyond where it used to be, and now it's 5 centimeters to the right of home. So it travels this way. So this is our particle traveling to the right. This is our particle traveling to the left. Then it sits still. And then here's our particle traveling to the right again. So let's talk about the position. Is easy to find. A position is just an ordered pair. So if I said, what is the position of the particle at time 4? You would tell me at 4 seconds. Let's call that S of 4. The position of the particle is -1. That means -1. That means 1 centimeter to the left of where it started. If you want displacement, displacement is change in position. So if I want the displacement from second 7 to 8, I would just do the change in position, right? So it would be S of 8 minus S of 7. Right, so at 8 seconds, it's at 5. At 7 seconds, it's at -2. And look how that negative kind of takes care of itself. So it moved from -2 to 5. It made a movement of 7 centimeters. That's just the displacement. We're just saying it moved 7 centimeters. So now, if we want velocity, we know that velocity is the derivative of position. So what that tells us is that when we're thinking about velocity, we're thinking about the slopes of the position. In other words, velocity equals the slope of position. So if I look from 1 to 2, we have a positive velocity because the slope is positive. So if I said, what's the velocity from 0 seconds to 2 seconds, or from 1 to 2, anywhere along this line, the velocity is a slope of 2 over 2. So the velocity at, let's just say at second 1, if I wanted to know the velocity right here, I I could look at the slope of this line, and I could say that if I figure out the slope of that line, it's 1. And that's 1 centimeter per every minute. And you could see that on the graph, or per every second, sorry. So we can see here, in the first second, it moves 1 centimeter. In the second second, it moves 1 centimeter. And it's moving in a positive direction. So then, if we want to know the velocity on this whole interval, the slope is the same the entire time. So that means the velocity on this entire interval is going to be, let's just say the velocity at 4. It's going to be the slope of this position function from here to here. And I mean, you can just count it if you want. So let's see, it goes down 1, 2, 3, 4, 5. And it goes over from 2 to 5, 3. So let's see, we went down 5, over 3. So it has a velocity of -5 centimeters per second. And we're calling it a negative velocity because the particle would be moving to the left. For this time interval, from 2 to 5 seconds, it moved from position 2 backwards or left until it got to position -3. So the velocity there is -5 over 3 centimeters per second. Here, the velocity is from the slope from 7 to 8. We can just count this again. We go up. In fact, we already found the change in position, right? 1, 2, 3, 4, 5, 6, 7, 8. So we went up 8. So I'll just call this V of 7. And over 1. So the velocity there was 8 centimeters per second, right? In 1 second, the particle traveled 8 centimeters to the right. So this is all what we call instantaneous velocity. That means I'm saying exactly what the velocity is at any given point, right? So even though this was from 7 to 8, that we had that velocity of 8, if I ask you what was the velocity at 7.3 seconds, the slope at 7.3 seconds is still a slope of 8. So the answer would still be 8. If I ask you what is the velocity at 6 seconds, this whole segment has a slope of 0. So that means we had a velocity of 0. And that makes sense. I mean, the particle didn't change position, so it can't have velocity. So let's switch for a minute and look at a velocity graph. And I'm going to keep my same axes, but I'm going to label them differently. So this time, and this is going to be a whole different scenario. This time, I'm going to call this centimeters per second. So this is a velocity graph. And this is still going to be seconds. So I'm going to just make up some points here. I'm going to look at how we went here. So I just put a point at 2, 4. Then I'm going to put another point at 4, -4. I'm going to connect those with a straight line. Then I'm going to put a point at, let's see, 6, 0. Then a point at 7, negative 3, and a point at 8, 5. So what I'm looking at is a velocity graph. And what this is telling me is at any given time, how many centimeters per second, let's say a particle again, is moving. And remember, when our particle is moving to the right, we're calling that a positive velocity. When our particle is moving to the left, we're calling that a negative velocity. So sometimes problems say moving forward instead of positive. Sometimes they say moving right, like I just did. Sometimes a problem is defined even with north and south. But we're going to stick with right for this. So if I ask the question, at what time intervals is the particle moving to the right? Or I think the question in the book said moving forward, but to the right, then because we're defining positive velocity as any velocity to the right, then that means that anytime these y values are positive, that the particle has positive velocity and is going right. So we could say the time interval from 0, I think I'd use parentheses, 0 to 3. And again, it's positive from, I can't really tell because I drew that line really messy. Actually, I don't know where that intersection is. I'm sure I could figure it out. 7 point something to 8 seconds, right? From here to here. If I'd drawn that better, it'd probably be easier to see. So that's when the particle is moving right on those time intervals. On these time intervals, the particle is moving left. So because we have negative velocity. So we'll say from 3 all the way to 6, and then from 6 to 7. Now, I made 2 intervals there because technically at 6, there's no velocity. It's a velocity of 0, so there's no direction. Okay. So the next thing we're going to look at is the acceleration. Actually, let's take a second and say, when was the velocity 0? The velocity was 0 at 3 seconds, 6 seconds, and 7 point something seconds. So the question then becomes, when does the particle switch directions? Well, if you're going to change directions, then your velocity has to switch directions. So right here, this particle was moving in a positive direction from second 1 to second 3. Right? It's moving this way, moving this way, moving this way. And at second 3, it shows a velocity of 0, and then immediately after that, it shows a negative velocity. So it changed directions here because it went from a positive velocity to a negative velocity. Okay, if the particle is moving this way, which would be positive, then turns around, this way is negative. So here's a positive velocity to the right, turns around, has a negative velocity to the left. At this instant, velocity is 0 at the turnaround point. Something interesting happens at 6. The particle is moving to the left. It gets a velocity of 0, and then it keeps moving to the left. You can see how the velocity stayed negative? Just think of it like a stop sign or something. It stopped, but it didn't switch directions. then here there's a velocity of 0 and the direction does change. The particle is going from a negative velocity to a positive velocity, so it must have switched directions. So a particle switches directions when its velocity is 0 and when the velocity sign changes. So you have to have both things happening. You have to have a velocity of 0 and you have to have the sign changing. So now let's talk about what velocity this thing was actually going. So let's analyze a few spots here. At 0.5 seconds, there was a velocity of 1 centimeter per second. At 1 second, there was a velocity of 2 centimeters per second. All I'm doing is I'm just reading the graph. At 1.5, we were 3 centimeters per second. And at 2 seconds, it was 4 centimeters per second. So this isn't position, this is actually speed or velocity. Okay, you're moving 1 centimeter per second. I mean, that's not all that impressive, right? Then 2 centimeters per second, well, suddenly 2 centimeters is about an inch in a second. We're getting some serious speed there. Then 3 centimeters the next second, so that's like 50% faster than before. And 4 centimeters at second 2. So, I mean, this thing is speeding up. Okay, and if you think of these like miles per hour, if I'm driving 1 mile per hour, then a second later I'm at 2 miles per hour, 3 miles per hour, 4 miles per hour, then you can tell that I am accelerating. So you know that something is accelerating when velocity has a positive slope. Because acceleration is the derivative of velocity. So if I have velocity and I take the derivative, I'll get acceleration. Oops, I did that backwards. Acceleration equals the derivative of velocity. So you can see that we were getting faster here. And you can see that we were getting faster at a specific rate, right? We were getting faster basically 1 centimeter every, half second? That's how much we're accelerating. In fact, that's the slope here. If you look, the slope is up 2 over 1, up 2 over 1. So the acceleration on the interval 0 to 2 was an acceleration of 2. Okay, because that's the slope of the velocity graph. And it's positive 2. So now let's look what happens from on the interval 2 to 4. And let's go ahead and put this here. At 2 seconds, the particle has a velocity of 4 centimeters per second. I'm just reading the graph. At 2.5 seconds, the particle has a velocity of 2 centimeters per second. Now these are still positive velocities. This particle is still moving right. It's just not moving as fast. Then at 3 seconds, the particle has a velocity of 0. At 3.5 seconds, if I just read the graph, it has a velocity of negative 2 centimeters per second. And then at 4 seconds, the velocity is negative 4 centimeters per second. Okay, because this is a velocity graph, the y values are actually telling me the velocities. If I want the acceleration on the interval 2 to 4, I could just find the slope. In fact, I can look at the acceleration at any point here. And since it's linear, it'll be the acceleration for the whole thing. So let's look at the acceleration at t equals 2.5. Well, acceleration is the derivative of velocity, and a derivative is slope. So at 2.5, we're part of this line right here. This line looks like it's going down 2 over 1, down 2 over 1. Remember, my scales are different, down 2 over 1. All right, great. So my velocity here is negative, or my acceleration is an acceleration of -2. So what that means is every second, I'm going 2 centimeters per second slower. So that means that we would call it -2 centimeters per second every second. So it's per second, which is weird. But I'm losing 2 centimeters of velocity every second. Right? I'm losing -2 centimeters per second every second. That's where it gets -2 centimeters per second. So I have a negative acceleration here. Then I have a positive acceleration here because velocity has a positive slope. So even though my velocity is negative, remember all that negative means for velocity is that it's moving left. So here it's moving left at a velocity of it's moving left at a velocity of -3 centimeters per second, at -2 centimeters per second, -1 centimeters per second, and then finally 0. So it was going -4 centimeters per second here. Then it sort of seems like it's slowing down, right? By here, it's barely moving, -1 centimeter per second, and then it just comes to a full stop. But then it starts up again in the same direction. So now it's still going left with a velocity of, what's this one? Like -2 centimeters per second, and then -3 centimeters per second. And then let's look at this acceleration from here to here. We're going from 7 to 8. And so let's just ask the question, what is the acceleration when t equals 7.5? And it's all the same for this entire line. So what you notice here is we go up, what is that, up 7. Oh, I ended up making this at the 0.4, that's why it was so hard. So we went up 7 over 1. So the acceleration here is an acceleration of 7 centimeters per second every second. So what got confusing in class today was when we started talking about speed. And here's all we have to remember about speed for now. Speed is the absolute value of velocity. Speed is always positive. So if I ask you what the particle's speed was at 5, you would tell me it has a speed of 2 centimeters per second. And remember, the policeman that stops me doesn't care if I'm heading north or south, doesn't care if my velocity is positive or negative. The police officer's radar gun just captures my speed. Okay, so 2 centimeters per second is the speed here. 2 centimeters per second is also the speed here. It's just in the other direction. So see how this is 2 centimeters per second? This is 2 centimeters per second. Velocity -2, velocity +2, but in both instances the speed is 2 centimeters per second. So that concept, I think, is straightforward. What ends up getting confusing is when we talk about these two terms, speeding up and slowing down. And basically, without doing the long explanation, it boils down to this. A particle is speeding up if velocity and acceleration have the same sign, like positive, positive, or negative, negative. And slowing down if velocity and acceleration have different signs. So when velocity and acceleration are working together, you are speeding up. So the example I gave in class was if somebody's falling, gravity is accelerating them as they go, and their velocity is in a negative direction. So they are speeding up as they fall because the acceleration force of gravity is working with the force of the velocity that they're already falling at. So every second, they're falling faster and faster and faster. Velocity and acceleration are the same sign. If I'm sailing my boat this way, let's call that a positive direction. So here's my boat. I'm sailing my boat in a positive direction, and think of the wind as my acceleration, then I'm speeding up. So I'm already going a certain velocity, but the wind is pushing me to go faster and faster. Okay, on the other hand, here's me trying to jump, and I'm jumping up with a certain velocity, but gravity is working against me. It's pushing me down. So I jump, and let's say I leave the ground at a rate of, 1 foot per second. By the time 2 seconds has passed, my velocity is down to 0. I have slowed down. I wish I could be airborne for 2 seconds. But I'm going to slow down as I go up. So let's look at that graph now. Right here, velocity is positive, right? These are all positive velocity values, and the slope is positive. So that means acceleration is positive. So I am speeding up here. And by the way, it makes sense. Positive velocity means I'm moving right. So as I move right, I'm going 1 centimeter per second, 2 centimeters per second, 3 centimeters per second, 4 centimeters per second. I was definitely accelerating. What happens here? I still am going right, but my acceleration, my slope has become negative. So though I'm still traveling to the right, 4 centimeters per second, 3 centimeters per second, 2 centimeters per second, 1 centimeter per second, all the way to 0 centimeters per second. So as this particle is going this way, it's getting slower and slower and slower and slower, and then at 3 seconds, it just stops. So you can think of this like it started up from the driveway, sped up, and then saw a traffic light coming up, slowed down, and stopped. It's still going the same direction. It just accelerated and then decelerated. But it made a U-turn when it was stopped. And now the velocity becomes negative. But the slope is negative, which is acceleration. So look, 0 miles per hour or centimeters per second, now negative 1 centimeter per second, negative 2 centimeter per second, negative 3 centimeter per second, negative 4 centimeter per second. Well, I'm moving left and my slope is negative. So getting faster and faster and faster. So I am speeding up here. So this was speeding up, positive slope, positive velocity. This was speeding up. This was slowing down. And now I'm speeding up again. Here I would be slowing down because I'm moving to the right, but my slope is positive. No, I'm speeding up. I'm sorry. Did I say speeding up? Yeah, I'm speeding up here. No, I'm not. I'm slowing down. I have negative velocity.